Okay, very good. Today we have Zahra from McGill University talking about non-relativistic physics in AdS and its CFT dual. We thank you, Zahra, for accepting our invitation, and please take it away.
Thank you, Joel. I want to thank you for inviting me. It's a great pleasure. So as Joel said, today I'll be talking about non-relativistic physics in AdS and its CFT dual. It's based on two papers with Henry Maxfield, which came out in the last few months. So the broad motivation of this work is to study, is to use AdS CFT duality as a framework to better understand quantum theories of gravity. Our approach is going to be a bottom-up approach in the sense that we are not going to look at the specific examples from a string theory, or rather we're going to postulate the duality as a duality between quantum gravity in d+1 dimensional asymptotically AdS spacetime and d-dimensional local CFT, which I depicted here pictorially. Here in the cylinder, I represent AdS in the cylinder time, right? So the time evolution in AdS, which is the upward direction on the cylinder, maps with radial evolution on the CFT, which is depicted by this radius thing between the two circle. However, it's been seen that it's challenging to use this duality to learn things for non-weakly interacting particles in the bulk. So our objective in this work is to address this issue by using the non-relativistic limit as a simplifying limit. So we go to non-relativistic limit, but we get the advantage that we can focus on non-perturbative interactions in the bulk. So that's the broad motivation. So non-relativistic limits, the point of it is that it provides us with a controllable setup in which we can do easy quantum mechanics in the bulk in AdS and learn about CFT spectrum in the bulk. And then the point is that this spectrum does not have to be close to mean field theory, and it can be away from mean field theory, which as we know, away from mean field theory, it's usually hard to get them because our perturbations usually around mean field theory. So in this talk, I'll present two problems which we explore in this setup. The first question is how to get the CFT double twist data for different bulk interaction or different non-relativistic bulk interaction. The second question is that what correlator describes lattice space scattering. So the full relativistic version of both of these questions have been of interest for many years, and many people have massively studied them in different limits. But here we'll focus on the non-relativistic version of these two questions. So let me start by talking about non-relativistic two-body problem in AdS. So the metric of global AdS is given as written on this slide, where f of r is a function which is, and the important thing is that it's quadratic in R, and L is the AdS curvature length. Global AdS, as I showed on the first slide, can be thought as a cylinder. We can see that by defining parameter radial coordinate rho such that it's related to R by tangent, through tangent of rho equal R over L. So pictorially, we then get the we then get the cylinder that I depicted in the first slide. And then we are interested in the non-relativistic dynamics. So if tau is the proper time of a geodesic in this background, we are interested in the dynamic where the spatial part of the velocity is much smaller than its temporal part. This in turn means that we can identify the time component of the metric as a gravitational potential, where here the gravitational potential can be written as a quadratic function because our metric dependent on R as a quadratic function. Here omega is given as C over L, where I remind you again, L was the radius curvature length. And it's important to see that this potential confines the dynamics of the non-relativistic particle to lie within R much smaller than L. So this means that we will not be the fact that we are at radius much smaller than at R much smaller than L means that the effect of AdS curvature is only going to be present to us through the harmonic oscillator potential, and we will not be able to probe the spatial curvature, the full relativistic curvature of the system, and the effect of curvature would be in this quadratic function, which comes from the temporal part of the velocity. Okay. For this limit to be self-consistent, we also need to study particles which themselves are non-relativistic particles. So we need the rest mass of the particles to be much larger than the quantum of the harmonic oscillator. Alternatively, we can say this as we need the quantum wavelength of the particles to be much smaller than AdS length. This means like we are localizing our particle in AdS. So this is the extra assumption that we put on our particles to ensure consistency. So for scaling dimension, imposing this would then imply that delta, which through the duality between delta and m is given as mc squared over h bar omega, then would be much bigger than 1, just because we impose mc squared to be much bigger than h bar omega. So in the non-relativistic limit, we are looking at operators in the boundary with a scaling dimension much bigger than 1. We can now write the Hamiltonian of the non-relativistic particles in AdS as follows. So for each operators that we have, we are going to have this harmonic potential. We're going to have a kinetic we're going to have a kinetic energy, and then we can have an arbitrary interaction between them, which I represent with V of R. And then since we're looking at the two-body problem, I goes from 1 to 2. And then this Hamiltonian would be the main object of our analysis in the bulk. So we're just going to study the simple harmonic oscillator plus another potential Hamiltonian, and then we're going to draw lessons from this for the CFT. Okay. So the outline of the talk is that first I'm going to review the symmetry of the problem. And then using that, I will describe how to prepare states through Euclidean time evolution. And then I will discuss what CFT correlation function is relevant in the non-relativistic limit. What's the dual of our non-relativistic dynamic in the bulk? And what's the CFT dual of that? And then I'm going to focus on the CFT, how to get information about double twist from the bulk. So for that, we're going to do a partial wave expansion in the bulk and S-channel decomposition in the CFT. And then we're going to map the two to each other and see how they relate. And then I will show that we can use this framework to get the free theory data as a first easy example. And then I'll also show the expansion around free theory from the bulk. So the expansion around mean field theory, how it works in our setup, and then I'll show you some of our results that it's away from mean field theory. And then we're going to check this double twist data that we got from the bulk from a calculation from the CFT side through inversion formula and other methods. At the end, I'll talk about the flat space scattering amplitude in the non-relativistic limit, how we can get that from our CFT correlation function. And that's going to be the summary. So if there are no questions, I can move to the symmetry of the problem. Okay. So as a starting point, we'll illustrate how to use the symmetry algebra, showing the decoupling of the center of mass and relative motion in our non-relativistic AdS setup. So the point of this symmetry analysis is that we want to show that we can decompose a non-relativistic symmetry group. We can use a non-relativistic symmetry group to decompose the non-relativistic Hamiltonian to a center of mass part, which only acts on the center of mass, and a relative part, which would include the important dynamic. So the symmetry algebra of AdS D+1 is the spaces, so D, 2, which is spanned by the dilatation operator, momentum operator, special conformal transformation, and rotation. Where the algebra is given in where the algebra is given here. And then this, in addition to this, we have the SOD algebra of rotation, which I didn't write explicitly, and along with the fact that Ki and Pi transform like vector under rotation. So now we want to take the non-relativistic limit of this algebra. And to do that, so when I'm saying non-relativistic limit, I mean non-relativistic limit in the bulk. There's a difference between non-relativistic limit in the bulk and in the boundary. I'm only focusing on the non-relativistic limit in the bulk. So and the point that and the reason that I can take this non-relativistic limit in the level algebra is that the dilatation operator is a generator of time translation in global coordinates. So it's the Hamiltonian in our AdS spacetime, and in the non-relativistic limits for particle of total mass m, then the Hamiltonian can be decomposed as the mass term, which is the biggest term, mc squared, because c goes to infinity, plus non-relativistic Hamiltonian. So this we can then use to simplify the algebra, because every term with mc squared is just going to commute with everything else, and the non-trivial part would be just the one coming from non-relativistic Hamiltonian. So using this, we can then simplify the algebra, which was written in the previous slide, to the 3 lines I wrote here, plus of course the rotation algebra. Algebra related to rotational symmetry. And if you look at this commutation relation long enough, you'll see that this is just the commutation relation for harmonic oscillator. And it's related to that by just a rescaling. So up to normalization, this is the algebra of harmonic oscillator with P with P proportional to the creation operator A dagger, and K proportional to annihilation operator A. And then the step that we need to take is that since Pi in the global is the momentum in the global coordinate, we can write it as a sum over xi and Pi, and then our creation operator Pi acts linearly in xi and Pi. Thus, then it means that this acts on the center of mass wave function, because it acts linearly on momentum and position. So from this, we can write the non-relativistic Hamiltonian as a center of mass part plus a relative part. Right, and then the center of mass part, as we showed, is just the harmonic oscillator Hamiltonian. So that's why we wrote it as a harmonic oscillator Hamiltonian. And then we can use the symmetry to trivialize the center of mass part. And this would mean to be in the ground states of the harmonic oscillator. So this means looking at states which are killed by A or K, special conformal transformation, and this by definition are primary states. So the states that correspond to the ground states of the harmonic oscillator are primary states, and focusing on those just means that we use the symmetry and we are in the ground state of the center of mass Hamiltonian. So the energy shift of the primary two particle states comes only from the relative Hamiltonian. So it's only enough for us to focus on the relative Hamiltonian if you're interested in the energy shift in the spectrum of the double twist operator of the two particle states. Since we can trivialize the center of mass by just looking at the ground state of this harmonic oscillator algebra. The fact that this is a harmonic oscillator showing up here, it shouldn't be surprising because we had the harmonic oscillator, we had our effect of curvature through this harmonic oscillator that showed up in the metric. Okay. Right. So now let's focus on how to prepare our particle states. So let's start by single particle states. So primary state O, which is dual to single particle, is operator inserted at distance Euclidean path on the cylinder or at the origin in the y plane. And then we can create a state at any other point at Euclidean time and angle by just time evolving, by just translation operator. So applying the translation operator, we can applying the translation operator to the ground state, we can prepare any other states that we want in the theory. We see that we get a coherent state after this evolution with the Gaussian wave function with the same width as the ground state, but a center offset from the origin. Applying translation operator to any primary state would give us a coherent state, which would be our any typical descendant state. Descendant particle state. So non-interacting two particle states would be a tensor product of these two coherent states, but this doesn't necessarily have to be a primary. To get a primary, we need to impose that this state is scaled by the special conformal transformation, and this is what we do here. So special conformal transformation can be decomposed for particle 1 and particle 2. And the eigenvalue of K acting on this O1, O2 state would be M1Y1 plus M2Y2. So imposing that this combination is 0 then means that the two particle state that we get is a primary double twist state. To get the primary two particle states, this is the condition we're going to impose. So the time evolution of the two has to the translation of the two has to be correlated. And this would create for us a generic two particle double twist two particle states in our non-relativistic limit. So this then motivates us to consider the Euclidean initial state psi n defined by a relative part and a center of mass part. Center of mass being in the ground state of the center of mass. I'm repeating, is just that we are looking at the primary we're looking at the primary two particle state. We are not going to lose any information by that. And then the relative part, it can be an arbitrary coherent state. So this would be our two particle states that we're going to use in our correlation function. So now we can write the Euclidean CFT 4-point correlation function, which is relevant for our non-relativistic limit as an overlap of these two particle states. So we're gonna prepare two particle states in the way I explained, and we're gonna look at the overlap of those, and this would then create us our 4-point correlation function, which would depend on tau, which is the total time, and theta, which is the angle between these two particle states. We can also look, instead of tau and theta, we can look at this as a function of z and z bar, conformal cross ratios. And we see that the conformal cross ratios would have to scale as 1 over reduced mass, which reduced mass is defined as this ratio of scaling dimensions. We see that in the non-relativistic limit, since delta is much bigger than 1 and mu scales as delta, for the non-relativistic limit, we see that we covered that z and z bar has to be much smaller than 1 with z delta kept fixed. So the limit that we are interested in is delta much bigger than 1, z much smaller than 1 with z delta fixed. That's the limit. Our CFT correlation function is governed by non-relativistic dynamics in the bulk. Okay. So from now on, we will be focusing on this correlation function, and we will study this correlation function. Okay. So let's see how we can get double twist data from looking at this dynamic in the bulk. So to get the double twist data from the bulk, we take 3 steps. First, we expand the correlator, the transition amplitude, as a sum over energy eigenstates of the Hamiltonian that we studied. Then we're going to show the equivalence of this expansion to the S-channel decomposition of the correlator. We then read off the CFT data in the S-channel by matching the 2 expansion. So that's going to be the procedure we're going to take. So what we want to show is that we want to show how we can write the transition amplitude between the coherent states, which was our 4-point Euclidean correlator, as a sum over Hamiltonian eigenstates. So the non-relativistic relative Hamiltonian can be written as follows. This is gonna where here everything that shows up is going to be in terms of mu, the reduced mass, which is what shows up in the relative Hamiltonian. For any potential V of R, note that we are not necessarily, okay, I can say that later, but let me say it here as well. We do not, the point of this study is that we don't have to assume that V of R is a smaller or yeah, it's the V of R can be as dominant as we want, and V of R does not need to be subleading to the harmonic potential. To get the mean field theory, we're gonna assume that the biggest contribution gonna come from the harmonic potential, but in general we don't have to, and we can study this Hamiltonian yeah, in a general case where V of R is as big as or as relevant as the harmonic oscillator part. So using the symmetry of the problem, the eigenstate of this Hamiltonian and the symmetry of the problem, I just mean the rotational symmetry, the fact that we can separate the radius part from the angular part. We can write the eigenstate of the Hamiltonian as a radial part plus an angular part. Whereas when R goes to infinity, this eigenstate would be exponentially would exponentially decay in R, and the reason for that is because when R goes to infinity, we're not going to see any effect of V of R because we assumed V of R goes to 0. Here, ALN, which is the coefficient here, is a real and positive coefficient, which is fixed by the normalization of the eigenfunction. And the energy dependence is in the power of the R squared term. So to get the correlator from the sum over states, then we're gonna, we just need the overlap of these energy eigenstates and our initial in our ingoing and outgoing states and our initial states, and this overlap we can calculate it because we have the explicit form of both the energy eigenstate at infinity and and this ingoing and outgoing states. And then this is going to be proportional to a Gegenbauer polynomial times something which has this energy dependence. The correlation function can then be written as a sum over all n and all l. This is, we can see, is just putting an identity, which is the sum over eigenstates inside the correlation function. And basically this that's how we get this expression here. You see that we had the normalization of the energy eigenstates squared here. And we have the same Gegenbauer polynomial that showed up here because it's just the sum over these overlaps. That's the expression we get if we put an identity inside our correlator. So then what we're going to do is we're going to decompose this correlator using S-channel decomposition. We're going to recover something very similar to this, and then we can interpret ELN and ALN, the terms showing up here, as OPE coefficient and scaling dimension, changing the scaling dimension. Okay. So this channel conformal block decomposition of the correlator, as that's familiar to the audience, is just given as follows, where the sum is over all states. We only have double twist states here because we are in the non-relativistic limit, and particle productions are not allowed. Taking the relevant regime in the non-relativistic limit, which is the large delta limit, with z delta fixed, the S-channel blocks would go as a Gegenbauer polynomial times this function of tau and delta. And then, having recovered this, we can match this to what the expression we had in the previous page to read off the OPE coefficient and read off the anomalous dimension of the double twist operators. And then, as I explained, by matching the two, we can read off the OPE coefficient and scaling dimension. Where you will see that the OPE coefficient is just proportional to the normalization of the wave function, and the scaling dimension of the double twist operator is given as a function of ELN as expected. So, right. If there are no questions, then I will use this for mean field theory to show, right, to show how this produces the correct mean field theory spectrum. Okay, so solving the free theory. So in our analysis, solving the unperturbed Hamiltonian, there is a free theory, gives us the free theory, OPE coefficient, and scaling dimension. In the case that V of R is 0, the Hamiltonian can be solved exactly, and the we can find our eigenfunction exactly to be this confluent hypergeometric function with eigenenergies as given as this function of n. And then using the correspondence that we saw in the previous page, we see that delta NL free would be exactly to what we expect from mean field theory. And the looking at the normalization of this phi NL that we have here, we see that the OPE coefficient that we recover is matches the result of the mean field theory in the large delta limit. So this is the, if you take the long expression for the mean field theory OPE coefficient and expand it at large delta, you see that you recover what we saw here. So that's nice to see that it comes about from a simple, very simple block calculation. Okay, we can then move on to expand around mean field theory, which would, in our language, corresponds to assuming that V of R contributes much less than the harmonic potential and it's subdominant. Assuming this, we can then use quantum perturbation theory to obtain energy shift from mean field theory spectrum due to the interacting potential. So the energy shift is given through a simple formula in quantum mechanics as written here. Here, NL I represented as the solution when V of R is 0. And then using the map, we see that the difference, this energy difference that we calculate through quantum perturbation theory is mapped to anomalous dimension. And using this analysis, we recover, using this analysis, we recover the anomalous dimension for double twist operators with the scaling dimension much bigger than 1. So let's see an example in which we can use this to get anomalous dimension, and then once we get the example, we can see if it matches what we get from the CFT. So for the case where the potential is linear in the coupling, we can separate the energy shift of different orders. In the coupling here, I represented as GN. And we recover that the anomalous dimension, the first energy shift would just be linear in V of R, and then the second order energy shift would be this formula. For the anomalous OPE coefficient to leading order is also obtained by varying the asymptotic decay coefficient A. And see how it changes when we have a small V of R, and then we can recover this relation between the anomalous OPE coefficient and the change in A, the coefficient A, which can be rewritten as the last line here. This is familiar to people in other contexts, but here we also recover it in the non-relativistic limit, that the change in anomalous dimension is a change in OPE coefficient is related this way to the anomalous dimension. Okay, so let's focus on an example with the first and easiest example with the Kepler potential in the equal 4, and this is just the 1/r potential, the simplest potential one can consider. And then performing the integral that are written here, we can recover the anomalous dimension, the first correction to mean field theory, the anomalous dimension, the first correction to the leading anomalous dimension as this 3F2 formula. So it's not illuminating to look at the 3F2 in the full generality, but I want to say that this 3F2 is not that scary because we have a minus integer here, which means that it's just a finite sum for any n. It's just a finite sum. It's not an infinite sum, so that makes it a little bit easier. We can look at different limits of this formula that would be to see that if it matches with what we expect. So a limit that we can take is the flat space limit, which is the large n, large L limit, where n is much larger than L. In the flat space, we see that we recover actually the right log of impact parameter that we expect from the Coulomb potential. So that's the first check. And we recover the log of impact parameter, which is the signature of the 1/r potential. In the large dimension limit, we get a power law behavior, however, which is expected in the large spin limit of the double twist. But note that this is not exactly the same power that we get in the largest spin limit from the light cone expansion. The power is different, and this comes from an order of limit things. So when L is much larger than delta, which is the relevant limit in the light cone expansion, we get 1 over L. But here, because we took delta large first and then L large, then we see that the L we recover is L to the 1/2. So it's power law, but it's a different power. And then we also, in our paper, we include the result for subleading anomalous dimension as well as anomalous OPE, which are complicated hypergeometric function, which I didn't write in this slide. The point of this is that so the anomalous dimension that we take is going to be valid for any n and l, which is nice. Usually when we get things from the CFT part, it's hard to get a large n form to get an all n formula for valid for all twists. But since the calculation in the bulk was so easy, we were able to read off the whole thing all at once. So what I'm gonna do in the CFT part is I'm going to drive this for a few first n and see that it matches with the relevant n. So if I take n, if I put n equals 0, 1, 2, I see that it matches with what I get from the from this formula. Okay. So this was for expanding around mean field theory. However, we can focus on other regimes and get the full Regge trajectory in the non-relativistic limit. Also, getting the full Regge trajectory is something that we are usually not able to do in the CFT. However, in the simplifying limit, we are able to get it because all the calculations are easy in the book. So the mean field theory plus the correction, we just saw how we get it. That would be the end part of this diagram for large L. At small l, the point is that we are going to be dominated by a flat space, by the flat space. We're not going to be able to see the effect of the harmonic potential so much. More the V of R would dominate. So the point is that we can do calculation where the V of when 1 over R is the dominant term, and then the harmonic potential is a subdominant. We can also use the WKB expansion, which is relevant because E over omega would be large here. Here, using that, we can recover the energy shift at small l when E is negative. We're going to have bound states, which would be our hydrogen atom. For small l, when E is positive, and we have is where we have the scattering states, and we're going to recover the Rutherford scattering states. For a slightly larger L, we're going to have classical system like a solar system or classical Keplerian orbits. And between solar system and where we can do mean field theory, where V of R, where 1 over R and the harmonic potential are of the same order, we can do numerical analysis and numerically determine the shift in energy and recover this region. So that way we can get the full Regge trajectory of the 1 over R when we have the 1 over R potential. Okay. Good. Then I'm going to move to the next part, which is how we can check this through a CFT calculation. The point is that right. So I'm going to discuss how we can get the things that we get close to the mean field theory from a CFT calculation. So here again, I'll just focus on what we get near mean field theory. So the perturbation discussed above has a nice interpretation as a number of graviton exchange in the cross channel. In the AdS correspondence, this then maps to the exchange of a stress tensor and its multi-twist operator in the CFT, and that's what we'll focus on. And we're going to use Lorentzian inversion formula, a formula developed by Simon to extract the scaling dimension and OPE coefficient of operators in CFT. Note that our analysis in the CFT part will be fully relativistic. But at the end, we can take the large dimension limit and match with what we had before. So we can use the Lorentzian inversion formula to get the double twisted spectrum, also order by order in GN. It's simple at order GN for the first few trajectories, but it's going to be harder for if we want to go to large N, to any, not large N, but to even intermediate N. So it's just going to be easier for a few first, and because it's an expansion in C, as we'll see. So Lorentzian inversion formula generates the CFT data from the double discontinuity of the correlator. Double discontinuity of the correlator is given as the Euclidean correlator, where its analytic continuation around the branch point is subtracted from it. And the point of this double discontinuity of the is that it's simpler than the correlator itself, so it can be calculated much simpler than the full correlator. And then this double discontinuity is what's going to encode our dynamical information in the Lorentzian inversion formula. So for us, the Lorentzian inversion formula is just a generating function which gets this dynamical information, which is this double discontinuity. It multiplies it by by an inverse block, which is just a kinematical object, and then it reproduces for us for its generating function, which has the anomalous dimension, which has the scaling dimension and OPE coefficient through its poles and through its powers and coefficient, which we'll see. So what is the inverse block? Inverse block is just the usual, which is the usual conformal block with its spin and scaling dimension swapped. And the point is that the double discontinuity of the correlator can be expanded in the OPE as well in terms of conformal blocks. Once we add this generating function that we get, which is a channel dependent thing, once we add the two cross channel results, we get the full generating function, and then the full generating function encodes the CFT data through its power and its coefficient. So the procedure is simple. It's just that take the dynamical part, which is in the double discontinuity, multiply it by something kinematical, do it for both cross channels, and then what you get, if you expand it in Z, you'll see that the powers of the Z expansion gives you the anomalous dimension, and the coefficients would give you the OPE coefficient. As you go further in expansion in Z, you'll recover the information about the M+1 rigid trajectory. So if you go further, you're going to recover other rigid trajectories with excited rigid trajectories, basically. Okay, so that's why it's harder to get rigid trajectory a bit higher and in the setup, because you have to expand in Z to higher power, and it becomes more complicated. So the procedure, as I said, is that expand the inverse block and double discontinuity in power of Z. Oh, I haven't said it, but the procedure is to expand the inverse block and the double discontinuity in power of Z to read the spectrum for each rigid trajectory. The advantage of this procedure is that at order G, only identity and stress tensor contributes to the double discontinuity of the correlator. The disadvantage is that the double expansion of the double discontinuity and the inverse block in power of z gets complicated if we look at excited rigid trajectories, and it's only easy for the first few n. And then there's the obstruction that the block do not admit closed forms in odd dimension. Our solution is to use geodesic Witten diagram to get integral representation for the stress tensor block. And then we can use collinear expansion for the kinematical part, which was the inverse block. So we use two expansion, one for inverse block, which would be the usual collinear block expansion, and then for the dynamical, for the part which contributes to double discontinuity, we're going to use the geodesic Witten diagram, and then we're going to expand inside the integral. So what is geodesic Witten diagram? Geodesic Witten diagram is a Witten diagram for a specific exchange operator with dimension delta and L, where we replace the integration over the bulk with integration along just the geodesic. This then produces the conformal block for dimension for scaling dimension delta and spin L. For the pairwise identical operators, this can be written as the following integral, where the integral goes over the two geodesics that are depicted by the yellow line. And then phi is the spin L propagator pulled back on the two geodesics. Using the symmetry in the global coordinate, we can then fix one of the geodesic to lie at a spatial origin r equals 0. And then the integral reduces to one integral, which is taken over the other geodesic and is given as follows. Here, H is the transverse traceless symmetric spin L representation. Sorry, here H is the transverse traceless symmetric spin L tensor solution to the wave equation. And using this, we can then calculate the stress tensor block in any dimension. So writing this explicitly gives us this formula, which we can use to calculate the stress tensor block in any dimension. We can expand it in any order that we want. With the above analysis, the inversion formula can be then analytically performed to give us the anomalous dimension in general, and also in the large delta limit, which is relevant for the non-relativistic case. And the anomalous dimension that we get from the inversion formula is the following gamma function. But the point is that if we check that matching this with the bulk calculation, the 3F2, these match, and they reproduce the correct f of t the correct f of t dependence on CT. On the central charge. So we can recover the correct central charge dependence of the OPE coefficient of the stress tensor. And indeed, what we calculated with the simple quantum mechanic analysis in the bulk were the correct result. So a few highlights. The first highlight is that repeating the calculation for conserved current of any spin give the same result up to normalization. So note that in the bulk, 1 over r didn't have to come from the graviton exchange, right? In the bulk, it could be an exchange of a photon. Any massless particle would give you a 1 over r potential in the non-relativistic limit. And we can indeed see that from the CFT part. So any conserved current exchange gives you the same result up to just the normalization, spin-dependent normalization. Doing the calculation above in general dimension doesn't introduce any further complication. And then we can also do the calculation with a scalar exchange with a large dimension. So if we assume that the exchange operator has a large dimension, the same order as the external operator, this then corresponds to the Yukawa potential. And then we can match what we get from the Yukawa potential in the bulk with what we get from an exchange of heavy operator in the CFT. And then we see that, again, we get a perfect match between the two. Okay, so I can now discuss the flat space scattering amplitude and how we get it from our CFT correlation function. So in order to probe the flat space region, we need to additionally take the extra limit that omega goes to 0, so that our dominant part, we don't see the effect of the harmonic, the effect of harmonic potential would be subdominant. Then since E over omega is large in this region, we can use WKB expansion to find the intermediate scattering states, taking the solution which matches to the flat spacetime scattering asymptotic. We get the following: we get a cosine function which is similar to the flat space scattering solution, except that this k here is not just the momentum; it has this this correction to it. And then from the WKB quantization condition, we can read the energy of these intermediate scattering states. And then we can then relate this using the correspondence that we developed between E and delta to see that gamma, the anomalous dimension, is proportional to the shift in energy here. To the phase shift. So this is also a known formula in other contexts, but we can also drive it in our non-relativistic limit. So the energy, okay, so the important part is the energy of these intermediate scattering states, which we will sum over to get the amplitude. Right, so we discussed that the overlap of these two particle states give us the Euclidean correlator. However, if we want to build the flat space scattering amplitude, we need to insert an additional real-time evolution. So in addition to evolving with Euclidean time to prepare the states, we need to consider an additional evolution in real time. This is depicted in the picture as follows. This hemisphere are there to show how we prepare the states by Euclidean evolving in time, and then evolving in the cylinder would be evolving in the real time. So the hemisphere are for evolving in the Euclidean time and the cylinders for the real time. And then if we put this additional real-time evolution, we see that this e to the minus I pi over omega h acting on the intermediate states would just give us this phase shift. Right, so to see why this is the correct flat space amplitude, we need to analyze how this expectation is realized by the sum over intermediate states. It's just again inserting a sum over identity, a sum over intermediate states, which is the identity inside the correlation function. So for a single intermediate state, by substitution, we get that this exponential acting on it, we just get the phase shift. Then we see that the intermediate states are indeed the partial amplitude in the flat space. And now summing over the partial amplitude gives us the full scattering amplitude and also the full scattering amplitude. So we see that if we sum over if we put an intermediate states, sum over intermediate states here and sum over all those, we get what we expected as the scattering amplitude in the flat space time. And we recover the flat space in the non-relativistic limit. So let me discuss, let me summarize what we discussed so far. In this talk, we analyzed the non-relativistic two-body problem in AdS. Specifically in this limit, we exploited the perturbation theory in order to extract data about the CFT spectrum. We found that the leading anomalous dimension of double twist operator, what it is when delta is much bigger than 1. We then use CFT tools to obtain the anomalous dimension for when n equals 0 and equal 1. And we found perfect agreement between the CFT calculation and the bulk calculation. We also introduced a physical way to extract the flat space bulk case matrix from AdS CFT correspondence. This has a few advantages compared to construction available in the literature. The first one is that since we use Euclidean time evolution in order to prepare the states, we did not need to smear in and out states over real time, which is what we would prefer. And we did not, so we can read the actual real time without needing to smear. We also did not have to treat VFR as a small correction because we had this split between mass plus center of mass plus relative, where mass is at the large parameter here. So the interaction can be as strong as we want, and we can go away from the mean field theory. Also, another thing that I didn't put in the slides, but I encourage you to look at in the paper is that if you're interested in the application of Lorentzian inversion formula, is that we obtain semi-classical and non-relativistic inversion formula. The non-relativistic inversion formula would be valid for large delta, and then the semi-classical one would be valid for large ln delta. These are the point of this is that these are much easier to evaluate than the full relativistic one, and since the kinematical object that we had here simplifies a lot. Also, the double discontinuity simplifies a lot in this limits, and basically we would just have exponential integrated against some easy function. Indeed, we performed our analysis in these limits, and we were able to go to way higher order in our calculation if we just, when we focused on this specific limit of the inversion formula. So if you're interested in large delta, you should look at this part of the paper. Future direction, I would like to discuss a little bit the future direction that one can take is that, non-relativistic dynamics turn out to be an easy toy model in which we can prepare the states, get the OPE data from partial wave decomposition, and do much more. It's thus perfect. It's the perfect playground to study the strongly coupled bulk physics from the CFT. Higher order in perturbation theory, we can go higher order in perturbation theory. We can, this would be interesting from the CFT perspective, as it gives contribution of the resummation of the multi-twist operator at single order. So the point is that we can, it's easier to go to higher order in the bulk since it's easy quantum mechanics, and then we can read off the result for resummation of the multi-twist operator at specific order. And then one can also try more general central potential to read CFD data in other regime or exchange other particles. One can look at radiation. Another thing is that we can also apply analysis in a top-down approach to a string theory setup. For example, we can apply an analysis for AdS 5 cross S5, take the non-relativistic limit of this, and learn what this implies for n equal 4, for instance. And with that, I want to finish my talk. Thank you for listening.
Thank you. All right, let's thank Zahra. Okay, I think we have time for questions. Any questions here? Okay, let me then go back basically to the beginning of the talk. Remind me, please.
Sure.
When you say that you have an harmonic oscillator, is that imposed or not? Because I think you presented something before. You said something like, I have an harmonic oscillator plus some central potential, and then you said that the conformal algebra would also be in that case would reproduce exactly the Hamiltonian for a harmonic oscillator. But right. Did you assume something, or it's?
So the harmonic potential came about from the metric of the metric of AdS. So if you look at this matrix, you have this quadratic term here, If you look at what potential this metric produces, so if you look at a geodesic in the background, in AdS background, and you take the you assume that this geodesic is moving slow, and in moving non-relativist, yeah, it's the speed is much smaller than c. Then the gravitational potential that you recover that's imposed on this particle moving slow in AdS background is this harmonic potential.
Okay.
So the gravitational effect, the gravitational effect of AdS background on a particle moving slowly in it is through this harmonic potential. It's kind of dictated by the by the metric.
Yeah, because my other question would be how much could you push away from non-relativistic physics? Like in this case, you would lose the potential, but and also
I think
it would also be much more complicated. I don't know.
So if you want to go away from the non-relativistic limit, that's a good question. So in flat space people do like post-Newtonian expansion. You can also do something here. You can expand this potential in the to higher order to higher order in 1/c, and then you're gonna get a correction to this. You will also get a correction, right? Probably from your, like if you look at the 1/r potential, you're gonna get a correction to that too. So you're gonna get a bunch of correction. Your Hamiltonian would become much more complicated, and then I guess in that way you can see 1/delta correction, right, to what you calculate in the boundary. That's a good question though. Thanks.
Yeah, I think it would be complicated to find the solutions, the states that you are preparing. It would be difficult, but still
it would be much more difficult. Yeah. Yeah.
Any other question?
So does this also constrain non-perturbative CFTs, like 3D easing model, for instance?
Could you
Okay.
list?
Great. Very good question. So I look at CFT. Right. So yes. The answer is yes. So you can. So the point is, the claim is, whenever you have large dimension, you can use this process. Okay, in the calculation that I gave here, and that was around mean field theory, I explicitly used that I'm around mean field theory, but I don't have to do that, right? I can use other. Because it's just quantum mechanics, I don't have to use quantum perturbation theory. I can use other perturbation that I have for when V of R is large, right? Okay, so if you want to apply this to any CFD, you have to understand you have to have some idea of the bulk, okay? Yeah, okay. So there are two things you can do. If you're only interested in the CFD part, you can look at the Lorentzian inversion, the non-relativistic limit, and all those. And if you know how is your block behaves in large delta and all those, then you can get information about large delta for any CFD. This does not have to have any bulk dual or anything.
Yeah.
So yeah, looking at the non-relativistic Lorentzian inversion formula or the classical inversion formula, you can always do that. You don't have to have bulk dual. And you can use those for large dimension operator for any non-perturbative CFD that you want. But in order to use the formalism that I discussed here, which was like bulk calculation, for that, you need to have some understanding of what the potential in the bulk is. And then once you know what the potential in the bulk is, then you don't have to assume anything about it being small or being it a perturbative. Yeah, you don't have to assume any perturbation around mean field theory or anything. You can be as far away from mean field theory as you want once you find what your potential in the bulk is. Does that answer the question?
Yeah. But is the block somewhat simpler? The inverted block in this limit, is it simpler?
It is
Then-
much simpler. Yeah, it's just an exponential. It's much simpler. Yeah.
Okay.
Yeah.
So inversion would be just kind of Fourier transforms. Okay.
Yeah, something very similar. Yeah, very simple. That's the point. Yeah,
Thanks.
sure.
Any other questions? Okay, if not, let's thank Zahra once again.
Thank you.
And we will stop here. Thank you, Zahra.
Thank you. It's nice seeing
See
you.
ya. See ya.